Okay, so today what we're going to do is we're going to go back to just manifolds, okay, plain old manifolds without a metric. And we're going to discuss a class of objects called differential forms. Okay, differential forms, these are objects which are defined on manifolds. And they're actually a subclass of tensors of with dual vector type indices. Okay, so what we do is our starting point is to consider tensors of type 0R. Okay, that is those with only dual vector indices at some point P on a manifold M. Okay, so again, note that we're not at the point where we have a metric space. We don't necessarily have a metric. Okay, we just have a manifold. And we take any particular tensor from the space. Okay, so this tensor space is defined as T0RP. Okay, so it's of type 0R at the point P. So 0 means that it has no vector-like indices. R is all dual vector-like indices. P is at the point P, M is the manifold M. Okay, and so what do we mean by this this tensor? Well, what it means is if we feed it R vector fields, okay, sorry, R vectors at the point P, then what it does is it's a linear map from these vectors to real numbers. Okay, so this omega is a multilinear map, which means omega takes in, for example, if you feed it a linear combination of two vectors and a third vector. Okay, so for example, this is a type 0, 2, 10 tensor at point P. And if you feed it a sum of two vectors at the point P and a third vector at the point P, okay, then what it will do is it will break up into this kind of combination. Okay, that's the definition of what we mean by a tensor. It's a multilinear map. Okay, so it will be A times W acting or omega acting on V1, V3 plus B times omega acting on V2, V3. Okay, that's how this splits up. And similarly, if you had put the linear combination in the second slot, you would have had a similar thing. Okay, so now what we do is, so these are just standard dual tensors, okay, tensors of type 0R. We've not yet got to forms. Okay, so what we're going to do first is we're going to define two operations that we can perform. Okay, these operations are denoted as P. And these are operations we perform on 0R tensors. Okay, and these are called symmetry operations. And what it does is it maps a particular tensor of type 0R at the point P to another tensor of type 0R again at the same point P. Okay, and the way it is performed is what it does is the definition of what we mean by P omega. Okay, so P omega is another tensor of type 0R, but the way this tensor is defined is by its action on vectors that you supply it as inputs. Okay, so if I supply it the vectors v1 through vr as inputs, okay, then by definition, what we mean by this P omega is that when it acts on this v1 through vr, what it gives you is just omega, but acting on a permutation of the v's. Okay, so P1, VP2, VPR, where P1, P2, PR are a permutation of the 1 through R indices. Okay, so PI is a permutation of the elements 1 through R. So to give an example of what we mean by these permutations, so if you have, for example, the indices 1, 2, 3, okay, so V1, V2, V3 are supplied as vectors. And I'll just talk about the indices. Okay, so forget about the fact that these are vectors. So just the indices 1, 2, 3. The permutation P1, P2, P3, what it means is, so one particular permutation is the identity permutation. That is, you don't change the ordering. But then you have other permutations. For example, I can change the 2, 3 elements with each other. So that's 1, 3, 2. Or I could have made a cyclic permutation that would be something like 3, 1, 2. Okay, and then these are the other combinations. Okay, so in total, of course, we know that there are 3 factorial permutations or 6 permutations. Okay, so these are the 6 permutations. Now you can assign a sign to each of these permutations depending on whether this permutation is obtained through an even number of exchanges of any two objects or an odd number of exchanges. Okay, so for example, if I want to get so let's start by default, the identity operation is assumed to have a sign +1. Okay, then all the other permutations have their signs automatically fixed by whether or not I need to, starting from this, if I need to go to this, I will make one exchange of 2 and 3, and that will give me an odd permutation. So that's -1. Then if I have 3, 1, 2, okay, that is again obtained by another exchange, so that every time I put an exchange, I multiply this sign factor by a -1. So this time I get a +1. Now I further exchange 2 and 1. Okay, so that will give me 3 to 1. That gives me a -1. Okay, and supposing I want to get 2, 1, 3, I could have just started with the original one and just exchanged the 1, 2 element, and I would got 2, 1, 3. So that's a minus sign. And from 2, 1, 3, if I want to get to 2, 3, 1, I would just exchange these two. Okay, I would get 2, 3, 1. And you could check that it doesn't matter which element you start with. If I obviously make an exchange, then I'm just counting the number of exchanges. So it's -1 raised to number of exchanges that you need to make to get from one permutation to another. Okay, so that defines what is called a sign of a permutation. And there are in total 3 factorial permutations. For 3 objects, okay, plus signs always are equivalent to cyclic permutations, and minus signs are anti-cyclic permutations. But that is specific to, plus signs are cyclic and minus signs are anti-cyclic. Okay, but that is specific to to 3 objects. When you go to higher objects, you don't really talk about cyclic and anti-cyclic, okay, because there are other combinations which you can obtain which are neither cyclic nor anti-cyclic combinations. For example, if I take 1, 2, 3, 4, anti-cyclic, well, what do we mean by anti-cyclic? Well, really what we mean is that we should perform an odd number of exchanges. Okay, so for example, if I do 1, 2, 3, 4, and I exchange first 2, 3. So I'll get 1, 3, 2, 4. So this will be a plus sign. This will be a minus sign. Okay, this will have a minus sign. And if I do another exchange, I get, for example, 1, 3, 4, 2. Okay, this is also a plus sign. But you see that this plus sign, this is not a cyclic permutation of 1, 2, 3, 4. Okay, so in 3 dimensions, in 3 objects, okay, cyclic permutations are associated with positive sign operations. But in higher number of objects, okay, the plus and minus signs, really you should count the number of exchanges that you need to get from an identity permutation to any of those other permutations. Okay, so so forget about cyclic and anti-cyclic. Only think about the number of exchanges you need to make to get from one combination to another. So each of these operations, okay, so let me call this P0, P1, P2, P3, P4, P5. So these are 6 operations that you can perform on the objects 1, 2, 3. Okay, and there are 3 factorial such operations. If I go to higher number of objects, so for example 4 objects, then I have 4 factorial operations that I can perform. Okay, half of them will be even operations, half of them will be odd operations in the sense that they pick up an overall minus sign. Okay, in this way of counting. Now, these operations P are elements of what is called a symmetric group. Okay, symmetric group of permutations of order R. Okay, which means that a combination of 2 successive operations is also some other operation in the same set, right? If I perform 2 successive permutations, that also gives me another permutation. And you know, it has other group properties that there's an identity operation and so on. Okay, so this defines a symmetric group called symmetric group R, which has 6 elements, or R factorial elements actually. Okay, this is the group of operations that you can perform. Okay, so now having defined an operation on indices, okay, we will now define this operation on 0R tensors. Okay, so the operation on 0R tensors, is by definition, okay, the operation on 0R tensors is when I supply it objects V1 through VR, it is equivalent to the action of omega, but acting on a permutation of the vectors V1 through VR. So I'm supplying them in different order over here. Okay, so I supply them in a different order over here. So, so what you can do now is we can obtain the components. Okay, so we'll do this in some kind of components. Okay, so we'll do this in if we take omega acting on epsilon mu1, epsilon mu r, sorry, e mu1, e mu r, where e mu1 is just a basis vector. It's a basis vector in the mu1 direction. E mu r is the basis vector in the mu r direction. So what that does is it gives us, so for example, if our omega in components looks like this in some coordinate basis, dx nu1 through dx nu r acting on e mu1, e mu2, e mu r. So these are the vectors that I'm supplying. Then what is going to happen is this dx nu1 will act on the first vector that you supply it, and that will produce a delta nu1 mu1. Okay, And so when I sum over the new one, what I'll get is this new one index will get replaced by a mu1 index. And similarly, all the indices get replaced by the corresponding indices. So the ordering matters, okay? The ordering matters and the ordering here matters. Okay, so you have to be careful about the ordering in general for a 0R tensor. Not every index is equivalent to, I can't just swap indices at will. Okay. So omega acting on this combination of basis vectors, okay, will give me the component omega mu1 through mu r. Okay, this is a component of this this particular dual tensor. So now what you can do is similarly, we can obtain the components of P omega. That is when we perform the symmetry operation on omega, where this operation P is in one-to-one correspondence with these symmetry permutations here. Okay. So what we do is P omega, we want the mu1 through mu r index. And we already know that this is already a tensor of type 0R. Okay. So if I want to obtain the mu1 through mu r index of any tensor of type 0R, what I will do is I will operate the tensor on basis vectors, okay, e mu1 through mu1. So we operate on the tensor on the basis vectors e mu1 through e mu r. By definition, okay, by definition, what we have is that this by definition is equal to omega acting on a permutation of these objects. Okay, that permutation is defined by the choice of this P. So the permutation of these objects is e mu of P1, e mu of PR. Okay, so P1 through PR. So for example, if this was originally I supplied mu1, mu2, mu3, and my permutation was such that it exchanges 2 and 1. So now what I have is mu2, 1, mu2, mu1, mu3. Okay, so if that was my permutation, then this is what I'm actually performing. And what I'm going to get, therefore, is omega acting on omega, the component of omega, mu P1 dot mu PR. Okay, so in other words, for example, if this was the permutation of exchanging mu2 and mu1, okay, or the 2-1 exchange, then this would have been equal to omega 213. Okay, this would have been the particular component that we would have picked out when we acted P omega on E1, E2, E3. Okay, instead of so omega acting on E1, E2, E3 would have given us omega 1, 2, 3. Okay, but P omega acting on E1, E2, E3 gives us omega 2, 1, 3. Okay, that is it's a permutation, okay, of omega. It's a permutation operation acting on omega. Okay. So you could have defined this not just for dual tensors, you could have defined this also for mixed tensors of type QR, but you have to separately perform symmetry operations on the vector-like indices and dual vector-like indices. You can't mix the permutations of vector type indices and dual vector indices, right? Because vector indices act on dual vectors. Dual vector indices act on vectors, so I can only permute vectors and I can only permute dual vectors. I can't permute between them. There's no natural correspondence between them on a manifold, right? But there's no metric. Okay, so I hope this operation P acting on omega is clear. Okay, and now we're going to use this operation to define two more operations. Okay, so one is called the symmetrizer. Okay, and one is called the anti-symmetrizer. So the symmetrizer is if I take a dual tensor of type 0R. Again, this maps me to a tensor of type 0R. The anti-symmetrizer also maps me to a tensor of type 0R. Okay. In both cases, S and A, what we do is let me define S of omega. So if given a tensor omega, S omega takes me to another tensor of type 0R. What I do is I sum over the permutations, all possible permutations of these R objects. Okay. And I operate those permutations on omega. So every possible permutation acting on omega, there are R factorial permutations. So I just average over those R factorial permutations. Okay, this is called a symmetrizer. Okay, so in other words, if I take the symmetrizer and I take its action, for example, suppose this is a type type 3 tensor, type 03 tensor. Okay, then I can feed it objects E1, E2, E3. And so omega acting on E1, E2, E3 is of course just omega 1, 2, 3. But now the symmetrizer acting on E1, E2, E3 will give me omega 1, 2, 3 plus omega 2, 1, 3, basically every possible permutation of these coefficients, omega whatever, 3, 2, 1, all 6 combinations divided by 1 over 3 factorial. Okay, so it's the average of all possible permutations of the coefficients. Okay. Now we also define something called the anti-symmetrizer operation. So the anti-symmetrizer acting on omega is 1 over r factorial. It's the same averaging, still averaging over permutations, except now we take into account the signs of the permutations. Okay. So if we take into account the signs of the permutations, so in components again, a omega acting on E1, E2, E3 would be something like 1 over 3 factorial. Okay, omega 1, 2, 3 would come with a plus sign. Omega, and then all cyclic permutations, okay, for 3 objects they would come with plus signs. So I would have 2, 3, 1 plus omega 3, 1, 2. But all the anti-cyclic permutations, which are obtained by odd number of exchanges, those would come with minus signs. Okay, so omega 2, 1, 3, omega 3, 2, 1, and omega 1, 3, 2. These would come with minus signs. Okay, so this is what the anti-symmetrizer operation is. Okay, it's averaging over permutations, but with a sign. Okay, so minus 1 raised to p is what we mean by the sign of the permutation. It's plus 1 for an even permutation, minus 1 for an odd permutation. Okay, and now we define a 0R tensor to be totally symmetric. Okay, 0R tensors can be arbitrary 0R tensors, but we define it to be totally symmetric if the tensor is equivalent to, if I perform the symmetrization on omega, I still get back the same omega. Then such a tensor is called totally symmetric. And it's called totally anti-symmetric if the tensor is equivalent to the anti-symmetry operation performed on omega. Okay. Okay, I'll just pause for questions at this point. Are these basic ideas clear? We'll work through some things in components. Okay, just to see what's going on. Okay, but are the basic ideas clear of the permutation operation, the symmetrization, and the anti-symmetrization operations?
Sir, I had a doubt. Okay, for tensors of type 0R, the whole thing is clear. But when we have tensors of the general tensor type, then how is PO acting on a tensor defined?
Okay, so then what we need to do is we need to define separately a permutation of upper indices. So if it's a tensor of type QR, okay, the permutations are permutations PQ, okay, which belong to SQ, the permutation group of Q elements, and let's say a P prime R, which are permutation group of R elements. Okay, so this is the permutation group. This is not the symmetrizer. Okay, so this is denoted as a script S typically, and this is denoted as script A. Okay, and this is like bold faces. Okay, this is the group of symmetry operations. So in this case, what we do is suppose you have a mixed tensor. Okay, the permutation operation, what it does is it permutes only the vector indices among themselves, and it permutes only the dual vector indices among themselves. Or for example, when we talk about a tensor of type QR, what we really mean is something that, so let me denote this object as T. It takes in Q dual vectors. Okay, it takes in Q dual vectors, which I'll denote as omega 1 through omega Q. And it takes in R vectors. Okay, so V1 through VR. So when we say that there's a permutation operation being performed on T, what we mean is, well, we have to specify which P operation and which P prime operation we're performing. These operations will actually commute with each other. So the order in which you do them will not matter. Okay, whether you do P or P prime or P prime first and then, sorry, P prime, whether you do P first and then P prime or whether you do P prime and then P, it won't really matter. What is going to happen is when you do the P prime operation, which is on dual vector indices, okay, what it does is it permutes these vectors. So it's going to be V P1, sorry, P prime 1, V P prime R. Okay, so it's going to permute these. And the P operation is going to permute these. So omega P1, omega PQ. Okay, and you can perform each separately or you can perform them in combinations like this. The order in which you perform them in combination does not matter.
Yes, that makes sense.
Yeah. In other words, we don't have to worry about the ordering of a vector-like index and a dual vector-like index. But we do have to worry about the ordering of all the dual vector indices amongst themselves and the relative ordering of all the vector-like indices among themselves. Okay. Okay. So now a couple of things. Okay. So for a totally symmetric tensor, okay, if we act a permutation on a totally symmetric tensor, we just get back the totally symmetric tensor. If this is an arbitrary permutation operation, okay, not the full symmetrizer. Any arbitrary permutation operation will give us back the same symmetric tensor. However, if we act the permutation operation, any permutation operation on an anti-symmetric, a totally anti-symmetric tensor, then what it does is it doesn't give you back exactly omega A. It gives you back omega A, that is the original anti-symmetric tensor, up to a sign. Okay, so if the original tensor is, sorry, if the permutation that you perform is an odd permutation, you'll get minus sign. If it's an even permutation, you'll get back a plus sign, okay, times the original tensor. Okay, so for the moment, we're only going to talk, and in fact, for this entire discussion, we're only going to talk about 0R type tensors. Okay. Why we're talking about 0R tensors will become a little apparent later when we define some operations on these 0R tensors, these particular 0R tensors, which will be some kind of new derivative which acts on these 0R type tensors. Okay, so finally, let me come to a definition. Okay, and the definition is rather simple now, if you understood the discussion so far. So a differential form, okay, of order R. So this is the object that we're going to be working with today, or an R form. Okay, so in short, it's called an R form, is defined as a totally anti-symmetric tensor of type 0R. Okay, that is, if you have a tensor omega A, which is, first of all, it has to be of type 0R. And the second thing is it has to be totally anti-symmetric, which means the anti-symmetry operator acting on this is equal to omega A. And any particular permutation acting on this will give me a signed version of the original omega A. Okay, so where this P is an element of the permutation group of R elements. Okay, so such objects. Okay, so instead of taking all possible 0R tensors, okay, we're considering a subclass of them, a subset of them, okay, which are anti-symmetric, totally anti-symmetric. Okay, that is in terms of components, they're anti-symmetric. In any pair of indices, they are anti-symmetric. Okay, so let me just tell you some points that follow from this definition. Okay, so the first thing is all dual vectors are automatically one forms, right? Because there's nothing to permute. There's only one object. Okay, so if you permute it, you'll get back the same object. So every dual vector is a one form. Okay, the space of all R forms at P is denoted as omega R PM. Okay, this is R forms at the point P on the manifold M. Okay, these are a subset. Okay, in general, they're a subset. Okay, they may be a proper subset or a non-proper subset. That is, they may or may not span the entire space of dual vectors of type 0R at the point P on the manifold M. Okay, so in the case of one forms, that is omega 1P M, this is identically equal to this all possible tensors. Okay, but for higher forms, that is omega p r m, you're only selecting the subset of totally anti-symmetric 0R tensors. Okay, so that's why it's a subspace. Okay, and the anti-symmetrizer A is actually a map. Okay, so instead of really being a map from T0 RPM to T0 RPM, it's really a map from T0 RPM to the subspace of T0 RPM. It's a map to forms. Okay, that is, if I supply a general 0R tensor and I act with the anti-symmetrizer, then the result of this operation, okay, let me call it psi. Okay, the result of this operation is a totally anti-symmetric tensor. Okay, and this totally anti-symmetric tensor is of type 0R, and therefore it's an R form. Okay, and this is a subspace. This is a subset of tensors of type 0R. Okay, at the point P. Okay, and you can generalize this to, instead of just talking about tensors at the point P, you can talk about tensor fields. Okay, so if your tensor fields are smooth, then the anti-symmetrization operation is also smooth. And so you can talk about not just at the point P, but you can talk about the space of all smooth dual tensor fields of type 0Rm. And the anti-symmetrizer, what it does is it takes us to a subspace of smooth R forms on M. Okay, so at every point P on the manifold, you're mapping to the anti-symmetric. You're performing an anti-symmetrization operation. Okay, and you and this is a subspace again of tau 0 M. Is this idea clear? So we've not constructed new objects. Rather, these are a subset of the objects that we're already familiar with. These are a subset of 0R tensors, okay, which are totally anti-symmetric. Okay, those are what we call smooth R forms. Is this idea clear?
Sir, like how does A act on any 0R tensor and make it an antisymmetric 0R tensor?
Okay, so let's go to the definition of A. Okay, A is this, right? So A acting on omega is this, okay? And we also called a tensor totally antisymmetric if when I act on this antisymmetric tensor with omega, I get back omega. So in other words, what we want to check, okay, is if I start with if I start with any general omega, which is of type 0R, I act with the anti-symmetrizer, I get a new tensor psi. Okay, my claim is that psi is a totally anti-symmetric tensor, which means A psi should be equal to psi. Okay, this is the claim. Or in other words, what we're claiming is, if we're claiming A psi is equal to psi, that means for any tensor omega, we're claiming that A square acting on omega is equal to A omega. Okay, or that is the operation A square is equal to the operation A. Right?
Yes, sir.
Okay, so so that we can show. Okay. Okay, again, I'll just work it out as a simple example. So for example, supposing again, we're taken omega, which acting on E1, E2, E3. So we'll just consider its action on E1, E2, E3. This is equal to omega 1, 2, 3. Okay. Now, if we consider A acting on omega, and this is a tensor again of type 0, 3, we'll consider its action on E1, E2, E3. Then this gives us 1 over 3 factorial times the signed combinations, right? it gives us omega 1, 2, 3. So all the cyclic ones will have a plus sign. All the anti-cyclic ones, like 2, 1, 3, these will have a minus sign. Right? And now we'll consider a square. Okay, so we'll consider a square omega acting on E1, E2, E3. Okay, and what this does is, now imagine that for each term, I can do it term by term, okay, because this anti-symmetrization operation is linear, okay. I mean, this is, so this, what I've calculated here is the 1, 2, 3 component of A omega. Okay, I've calculated the 1, 2, 3 component of A omega, which is this. It's related to the components of the original omega. Okay, so now if I'm calculating A square omega, so I'm calculating A square omega, now I'm calculating the 1, 2, 3 component of this. Okay, and this is the 1, 2, 3 component of omega. Okay, this will now be equal to A omega, okay, 1, 2, 3 plus A omega 1 over 3 factorial. A omega, so again, the cyclic permutations will have plus signs. So I'll have, for example, 3, 1, 2 plus A omega. Then I'll have, instead of 1, 2, 3. So now, sorry, now for the odd permutations, I will have something like this. Okay, and then I now have to further use what I derived about these A omegas. Okay, and what we will get is something like, so this one will be expanded into 6 terms. This, okay, so it's 1 over 3 factorial, and then there's another 1 over 3 factorial times, now I'll have 6 terms. So there'll be like omega 1, 2, 3 plus, you know, again, all even permutations will come with plus signs, odd permutations will come with minus signs. But I also have to expand this. Okay, I have to expand A omega 3, 1, 2. And now when I expand A omega 3, 1, 2, what I will get is 1 over 3 factorial. And now I have to take the 3, 1, 2 component of this. So basically think of exchanging the 1, 2, 3 indices. But again, the positive permutations will always come with a plus sign. Okay, so this one will become omega 3, 1, 2. Okay, that's the first term in this expansion. Okay, but the positive combinations will always come with a plus sign again. Okay, it's a combination of 2 positive operations. Okay, it's this positive operation and this positive operation. So positive permutations will all come with a plus sign. Okay, and negative permutations will again come with a minus sign. Okay, so this will be 1, 3, 2, and so on. Okay, but somewhere in this 1, 3, 2 permutations, again, I'll get a omega 2, 1, 3. So all the so like this, I'll expand. I'll have 6 terms here. Each of these 6 terms is expanded further into 6 terms. Okay, but again, these are composed of the same objects. These are symmetric combinations. These are anti-symmetric combinations. Okay, so at the end, you can add them all up. Okay, you can, I mean, there are only 6 unique combinations that you can have. So we'll have 1 over 3 factorial. And this 1 over 3 factorial is basically 1 by 6. And now I'll take the omega 1, 2, 3 from here. There'll be an omega 1, 2, 3 here. Each of these 6 terms will have an omega 1, 2, 3. So 6 times omega 1, 2, 3 divided by 1 over 3 factorial will just give me omega 1, 2, 3. Similarly, all the even permutations will just give me this. Okay. Similarly, the odd permutations will give me this. Okay, 2, 3 minus omega 1, 3, 2. Okay, and so on. Okay, so all the odd permutations will give me this. So what I get at the end is just one. This is basically just A omega. So A square omega for any, you know, I mean, these E1, E2, or E3 are quite general, but A square omega acting on any general E1, E2, E3 will be equal to A omega acting on E1, E2. Okay, so we've just proved that A square is equal to A. Does that make sense?
Yes, sir.
Okay, so now we're directly starting with objects which are R forms. We're not constructing them by anti-symmetrization. We directly start with anti-symmetrized objects. Okay, objects which are already anti-symmetric. So these are R forms. Omega R. And now what we can do is we can define operations between different R forms. Okay, so remember that these are just a subclass, a subset of operations of type 0Rm. So what we can do is we can define something called a wedge product. Okay, this is denoted by this wedge type symbol. Okay, it's a wedge product of differential forms, or it's also called an exterior product. So the wedge product is defined as you start with two forms. One is of type R1, one is of type R2. Okay, and it's a generalization of the tensor product. We already know if you have a tensor of type 0R and another tensor of type 0R2, you know how to take the tensor product of these two tensors. Okay, so what we want to do is we want to, but the tensor product lies in the space of tensors of type R1 plus R2. Okay, what we want to do is construct a wedge product which takes us from tensors of, R1 forms and R2 forms. Okay, and if I feed it an R1 form and an R2 form, it should return for me something that is an R1 plus R2 form. Okay, now the way we do this is we define omega 1 wedge omega 2. Okay, as the first we take the tensor product of omega 1 and omega 2. Since these are tensors, okay, of type 0R, you can always do this tensor product. But this tensor product need not be anti-symmetric, okay, because it's only anti-symmetric, totally anti-symmetric in the omega 1s and totally anti-symmetric in the omega 2 indices. But it's not anti-symmetric under exchange of omega 1 and omega 2 indices. So what we need to do further is we need to apply an anti-symmetrization operation on this tensor product, okay, of omega 1 and omega 2. Okay, and then for convention, okay, and we'll see why this convention is useful later, we define it by multiplying it by this combination of permutations, 1 over R1 factorial, which is the number of ways you can permute the omega 1 indices, 1 over R2 factorial, which is the number of ways you can permute the omega 2 indices, times R1 plus R2 factorial, which is the number of ways you can permute all the indices of this combined tensor product object. Okay, so this is a conventional choice. Okay, but the key thing is when I take the normal tensor product, I will not get a totally anti-symmetric object. Only when I anti-symmetrize it, then I'm going to get a totally anti-symmetric object, and then I'm guaranteed to be in this space. Okay, the space of R1 plus R2 forms. And this is a normalization convention. Okay, the rest of it. Okay, but we'll see that this is a useful normalization convention. Okay, so this is an operation, okay, that you can perform. Okay, I mean, you could have written it as I feed in an omega 1 and an omega 2, but later we'll see that this wedge product can be thought of very similarly to multiplication, except it's not a commutative multiplication. It's commutative up to a plus or minus sign. So that is just as how we take the multiplication of any two real numbers, Q and R, okay, and we write it as Q dot R. Okay, this is really, you can think of it as an operation which takes in two numbers and gives me a third number, right? Similarly, this takes in two R1 and R2 forms and returns an R1 plus R2 form. We'll see that this can be thought of as a product, okay, except the product is not commutative, which means that if I feed it omega 1, omega 2, this will not necessarily be the same as omega 2, omega 1. Okay, it'll be the same up to a plus or a minus sign. Okay, so that's why we write the wedge product in the middle between these two objects. Okay, but really, if you like, you can think of it as acting on the two objects. Okay, to prove some properties of these differential forms, what we're going to do next is we're going to work in a particular coordinate patch. Okay, but some of the results we derive will be quite general. They'll be valid, and we'll see why. Okay, we'll see that these results are defined. So this anti-symmetrization operation, the symmetrization operation, clearly these are defined independent of any coordinate patch. Okay, because I can always permute the vector fields that I supply to an object. But it's just going to be more useful to kind of visualize this in a particular coordinate patch. Okay, but the main results that we get will be independent of any choice of coordinate system that we impose. So let's consider a basis of dual vectors. Okay, so let's consider many dual vectors of the form dxu1, dxu2, dx mu r. So this is the basis of dual vectors in a particular coordinate system. Okay, where mu1 through mu r are fixed indices. These can be repeated. For example, if I'm in x, y, z, mu1 could be x, mu2 could be y, but mu3 could again be x. Okay, so this is just some choice of mu1, mu2, and mu r. R is not necessarily the number of dimensions of the space. The number of dimensions of the space will denote as n. Okay, and in general, at the moment, R can be greater than n, R can be less than n, R can be equal to n. I mean, all these possibilities are allowed. Okay, so these are R1 forms. Okay, so these are R different one forms. Okay, why? Because firstly, they're dual vectors. All dual vectors are automatically anti-symmetric, and therefore they are one forms. Now what we can do is let's construct the wedge product. Okay, so let's take two of these dual vectors. So let's say dx mu1 and dx mu2, and let's construct the wedge product. So dx mu1 wedge dx mu2 is by definition, first we take the tensor product of dx mu1 dx mu2. Then we take the anti-symmetrizer acting on this, and then we multiply by 2 factorial and divide by 1 factorial times 1 factorial. Okay. The anti-symmetrizer acting on this gives me 1 over 2 factorial, and now I permute these indices. So it's dx mu1 tensor product dx mu2, and now I permute the indices minus dx mu2 tensor product dx mu1. Okay, times this out thing 2 factorial over here. So this is why the 2 factorial is normalization is useful. This cancels out here, and what you get is minus dx mu2 tensor product dx mu1. Okay, so sorry. What I meant to say is this. So what it is it's actually equal to dx mu1 tensor product dx mu2 minus dx mu2 tensor product dx mu. Okay, so this is what we mean by this wedge product. Okay, of two one forms. Okay, this has given us something that is a 0-2 form. Sorry, a 2 form. Okay, it's a 2 form because it is firstly it's a type 0-2 tensor. Okay, at the point P, but it's also a fully anti-symmetric 0-2 tensor. Okay, which means if I feed it any v1, v2, sorry, if I operate with the anti-symmetrizer on this, okay, I will get back the same object. Okay, so it's already fully anti-symmetric. Okay, so this now what you can also see, for example, is if I had exchanged the mu2 and mu1 indices. Okay, so if I had evaluated this dx mu2 wedge dx mu1, that would have exchanged the mu1 and mu2 indices here, and it would have exchanged the mu1 and mu2 indices here, which means I would have got an overall minus sign times this original quantity. So that tells me that dx mu1 wedge dx mu2 is equal to minus of dx mu2 wedge dx mu1. So this is what I told you, that the wedge product is not necessarily a commutative product. It can be commutative or it can be anti-commutative. Okay, so we'll see the conditions under which it's commutative and the conditions under which it's anti-commutative. In this particular case, the product of two one forms is anti-commutative. Okay, it gives me minus dx mu2 wedge dx mu1. And these objects, okay, that we've constructed. Okay, so if I take mu1 belonging to any one of 1 through n, mu2 belonging to any one of 1 through n. Okay, all such unique objects that I can construct. Okay, this gives me a basis of two forms. Okay, so just like dx mu1 tensor product dx mu2. Okay, for any choice of mu1 and mu2, this is a basis of tensors of type 0-2. Okay, this wedge product gives me now a basis of two forms. These are specifically the fully anti-symmetric tensors of type 0-2. Okay, so this is anti-symmetric tensors of type 2 on the manifold M. Okay, at the point P. So these are two forms. Okay, this is a basis of two forms. Okay, similarly, you can construct a wedge product. Okay, so now that we have dx mu2 wedge dx mu3, which is a general basis element of omega 2 pm, we can now take a 0-2 or 2 form, omega 2. Okay, and we can take a wedge product with a 1 form. Okay, and the way we take this wedge product is, again, we take the tensor product of this with this. So it's useful to write this again using the original tensor product notation. Okay, dx mu2 tensor dx mu3 minus dx mu3 tensor dx mu2. And now on the outside, I have dx mu1 tensor this. But this product is not fully anti-symmetric. So I need to further anti-symmetrize this. Okay, and then I multiply again by these conventional factors of 3 factorial. Why 3 factorial? Because this is 1 forms, 2 forms, so 3 factorial, divided by 1 factorial and 2 factorial. Okay, so what we're going to get at the end when we anti-symmetrize this is, so first let me take this tensor product. So I'll take dx1 tensor dx mu2 tensor dx mu3. Okay. Okay, you can show with a little bit of work, okay, that this anti-symmetrizer when it acts on this will give me minus dx mu1 tensor dx mu2 tensor dx mu3. Okay, and again, the even combinations will all come with plus signs. Okay, the even combinations will all come with plus signs. The odd combinations will come with minus signs. Okay, and these factors which are chosen for convenience, the 3 factorial will cancel with the 1 by 3 factorial that comes from the anti-symmetrizer. Okay, and the 2 factorial will cancel with the fact that I have 2 different terms with which I'm taking this tensor product. Okay, but each of them will give me the same thing once I anti-symmetrize, once I fully anti-symmetrize. Okay, so that's why these factors were useful. Okay, so what you get here is something like this. Okay, and what you can see is that this dx mu1 wedge dx mu2 wedge dx mu3, it wouldn't have mattered whether I had first done this inner product or I first did this inner product. Okay, so this exterior product. Okay, the wedge product I mean. Okay, not inner product. Okay, we'll define something else called the inner product later. Okay, so we are strictly talking about the wedge product here. So this is dx mu1 wedge dx mu2. Okay, if I'd done this first and then done wedge dx mu3, this would have given me the same thing. Okay, so so this wedge product is associative. Okay, but it's not commutative. And in this case, this dx mu1 wedge dx mu2 wedge dx mu3. Now I don't have to put the brackets around anything because the order in which I perform the wedge product, whether I perform this first or this first, doesn't matter. So I won't put the brackets around anything. So now when I take this, okay, this is a general basis of 3 forms. Okay, this is a general basis of 3 forms. So now you're starting to see the idea, right? If I want to construct the general basis of R forms, the general basis of R forms will look like this. Okay, for any choice of mu1 through mu r. Okay, for all possible choices of mu1 through mu r. But remember that not every choice is distinct from every other choice. Okay, so we'll do counting of how many unique basis elements there are. Okay, for example, we've already seen that dx1 wedge dx2 is the same as minus dx2 wedge dx1. So these are not linearly independent basis 2 forms. Okay, so we want to count the number of linearly independent basis R forms. Okay, so we'll see how to do that counting in a moment. Okay, so first some general properties of this wedge product. So the first thing is it's associative, okay, which we already showed. Okay, it's also linear, which means if I take the wedge product of A omega 1 plus B omega 2, wedge omega 3, wedge omega 4, I can first perform, I can expand this out as A omega 1 wedge omega 3 wedge omega 4. Why is it linear? It's linear because the tensor product is linear. Okay, so because the tensor product operation is linear, this operation is also linear. It's totally anti-symmetric. Okay, which is if I take dx mu1 wedge dot 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 wedge dx mu r, this is a totally anti-symmetric tensor of type 0r. Okay, which means that this is related to if I permute the indices of the mu1 through mu r using some particular permutation where P belongs to the permutation group of R elements, then I will get back, sorry, not this. Dx mu, dx mu, dx mu. But now I've shuffled the indices. I've shuffled these objects. Okay, these 1 forms. And now I get minus 1 raised to P, where this is the sign of the permutation. Okay, because this is a totally anti-symmetric object. Why the totally anti-symmetric object? It's obvious by the definition. It's an anti-symmetrizer acting on on a tensor product. Okay. And finally, if I have dx mu1 wedge dot 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 wedge dx mu r, if any two of these mu i's are the same, okay, for example, if I've done dx wedge dx, okay, we've already seen that this is minus dx wedge dx. So this is 0. Okay, because if an object is minus of itself, then it's 0. So so in fact, if any two of these mu i's are the same, because it's a totally anti-symmetric object, okay, if I exchange those two objects with each other, okay, because it's a totally anti-symmetric object, this is just 0. Okay, so if any two mu i's and mu j's are equal, then this object is just 0. Okay, so now what we're going to do is we're going to try to find a basis, okay, for R forms. Okay, and these basis elements are of this form. Okay, but we need to figure out what is a good choice of the mu ones. Okay, of course, these can be selected from any values from 1 through n, where n is the dimension of the manifold. Okay, but not every choice, as we've seen, is going to give us a unique basis R form. Okay, so the set mu1 through mu r has to be unique up to a permutation. Okay, because if I change the ordering, okay, then I will get back the same basis vector up to a plus or minus sign. So therefore, the choices of these, okay, which are from 1 through n, this is through 1 through n, the choice is unique up to a permutation. So for example, in 4 dimensions, okay, if n is equal to 4, and if I'm working with two forms of type 0 to 2, then I just need to choose, okay, the first element, okay, I can choose in n ways. So if I'm choosing two forms, okay, my two forms have two indices. They have the basis vectors look like this. Sorry. The basis of R forms looks like this. Mu1 can be chosen in n ways. Mu2 can be chosen in n minus 1 ways. But the ordering of these two doesn't matter, so it's divided by 2 factorial. Okay, so in other words, I have dx1 wedge dx mu2. This is one basis element. dx1 wedge dx3, dx1 wedge dx4, dx2 wedge dx3, dx2 wedge dx4, dx3 wedge dx4. Okay, in general, for n dimensions, the space of R forms is a vector space of dimension ncr. Okay, so there are n choose R basis vectors. So you can think of it as n factorial. Okay, that's the number of independent permutations I have. Okay. Sorry, the number of unique permutations that I have is n choose R. Okay, because I need to choose R of them. I just need to choose R objects and I don't care about the ordering of those objects. Okay, so it's n choose R, okay, which is n factorial by R factorial into n minus R factorial. Okay, and it's a vector space just in the sense that any tensor space is a vector space in the sense that it's linear. Okay, and I can add up two tensors and get back a third element of that same space. Okay, so when I say vector space, I mean it in the more general sense, okay, of what we mean by vector space. Okay, any questions at this point? Can you hear me? Hello?
Sir.
Sir.
Yeah, something seems wrong with my desktop. Okay, if you can hear me here, I'm just on my iPad. I'll just continue from here. Is that okay?
Yes, sir.
Okay. Okay, so is the audio clear?
Yes, sir, it is clear.
Okay, so now what we do is the vector space of R forms and n minus R forms are actually isomorphic, okay? Because if any vector space has B elements and another vector space has B elements, they're always isomorphic to each other, okay? Now, it's not, I mean, what is the exact isomorphism? Like, what is the mapping between these vector spaces? That will come to later. But what that means is this vector space has n choose R basis vectors. This vector space has n choose n minus R basis vectors, but this is also equal to NCR, which means that the number of basis vectors of R forms is the same as the number of basis vectors of n minus R forms. Okay, and therefore these two vector spaces are isomorphic to each other. Okay, we'll see what the exact isomorphism is or the mapping between R forms and n minus R forms is later. Okay, but this is actually going to be a very important result. Okay, so now if you have a general R form, it can be expanded as this. So if I have a general R form, omega, it can be expanded in terms of these basis vectors. Okay, these dx mu1 wedge dot 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 dx mu r, where these mu1 through mu r are any of those n choose r basis vectors. Okay, so I choose any one unique choice gives me one basis vector of the space of R forms. And these are coefficients, omega mu1 through mu r, and I divide by 1 by r factorial. That is just a convention choice, okay, when I define this way. So we'll see why this convention choice is useful. So we choose the coefficients, omega mu1 through mu r already, okay, so we don't have to choose these coefficients to be totally anti-symmetric, but without loss of generality, we can choose them to be anti-symmetric, totally anti-symmetric, which means if I exchange any two indices, okay, depending on, if I make an odd exchange, so if I just exchange mu1 and mu2, this is equal to minus omega mu1, mu2 through mu r. Okay, and in general, omega mu1 through mu r is minus 1 times, minus 1 raised to p. This is the sign of the permutation, where I exchange, these r indices by shuffling amongst themselves using some particular permutation. Okay, so if I choose this definition, you can see that now if I expand out this wedge product using tensor product, so we've seen that this is expanded out using a fully anti-symmetric combination of these tensor products. So this is dx mu1 tensor dx mu2 tensor dot 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 tensor dx mu r. Okay, then this is by definition, okay, actually equal to dx mu1 tensor dx mu2 tensor dot 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 tensor dx mu r, but without the 1 by r factorial, and now I just have the omega mu1 through mu r. Okay, so if you see what we've done here, initially we had a wedge product, now we just have a tensor product. Okay, what happened to the anti-symmetry of these mu1 through mu r? That anti-symmetry is already guaranteed by the anti-symmetry of the coefficients. So if we choose the coefficients to be fully anti-symmetric, then this becomes automatically anti-symmetric, totally anti-symmetric when I sum over the mu1 through. Is this clear? Can you hear me?
Yeah.
Okay. So, so for example, let's start with a general rank 2 tensor. Okay, so we start with a general rank 2 tensor. This is not necessarily a 2 form. This is just a tensor of type 0, 2. Okay, so it has a dx nu, and there's an omega mu nu coefficient. So any omega mu nu, okay, can always be written as half omega mu nu plus omega nu mu plus half omega mu nu minus omega nu mu. Okay, this is just moving around indices. So these two terms add up, okay, and give you omega mu nu. These two terms cancel and give you minus omega mu. But the point is that these coefficients, if I break it up into these parts, okay, so if I define this as the symmetric combination of omega mu nu and omega nu mu, which I write like this, and I call that sigma mu nu, this denotes the symmetric part. And if I define the anti-symmetric part as this combination, which is omega with square brackets mu nu. Okay, so you can think of it as the square brackets tell me that I have to anti-commute indices. So whenever any two indices are I make an odd number of permutations, I pick up a minus sign. Okay, and I 1 by 2 factorial, 1 by 2. In general, if I have omega mu1 to mu r, and if I want to take the symmetric combination, what I'm really saying is I will write down, a permutation mu p1, mu pr. I will always use a plus sign, and I'll use a 1 by r factorial. Okay, this is a generalization of so the symmetrization, anti-symmetrization operations were defined directly on tensors. Here we're talking about something which is performed on the indices. Okay, this is 1 by r factorial summation over permutations minus 1 through raised to r, and then omega mu p1 through mu pr. Okay, so this is what we mean by these square brackets. You'll see this often in GR books. Okay, where you use these circular brackets or regular brackets for symmetrization of these indices, and the square bracket for total anti-symmetrization. Okay, so this is the anti-symmetric combination, and this was the symmetric combination, and any 0-2 tensor can be broken up into a totally symmetric and a totally anti-symmetric combination. Okay, for higher tensors, you can't always break it up into a totally symmetric and a totally anti-symmetric. There will be terms which are partially symmetric, okay, which are not fully symmetric or fully anti-symmetric. Anyway, so now what we can do is we can write this omega mu nu dx mu tensor dx nu. Okay, we can write it as this omega mu nu is split into two parts. It's the sigma mu nu, which is the symmetric part, and alpha mu nu, which is the anti-symmetric part. So we'll write it as alpha mu nu times dx mu plus sigma mu nu dx mu. Okay, sorry. What I really wanted to write was the wedge product here. Okay, now because this wedge product is anti-symmetric, okay, because the wedge product is anti-symmetric, if I take symmetric combination of indices contracted with anti-symmetric combinations of the indices, I'm going to get 0. So this term will just vanish. And so this quantity will just be equal to alpha mu nu, the anti-symmetric combination, dx mu wedge dx nu. Okay, so in other words, if we had started without loss of generality, we can take omega mu nu, okay, in this kind of so if we start with a form, omega is equal to omega mu nu dx mu. Without loss of generality, we can take omega mu nu to be totally anti-symmetric, because any other combination which is not totally anti-symmetric would give me 0 because of the total anti-symmetry of the wedge product. Okay. Okay, so without loss of generality, we'll always choose these coefficients to be totally anti-symmetric inside R forms. Okay, so in general, omega mu1 through mu r is assumed to be totally anti-symmetric. Okay, that is, this is equal to omega mu1 through mu r. Okay, we'll assume this without loss of generality. Okay, so by definition, we take the space of 0 forms, okay, to just be real numbers. Okay, the space of 1 forms are dual vectors. And now we can extend these. Of course, we've talked about how to extend them to smooth forms. That is not just at the point P, but over the entire manifold. So if you want a basis of R forms, okay, omega 0 P M, that is 0 forms, are just smooth functions on the manifold. So we can think of their basis as just the real number 1, okay, and they have dimension 1. 1 forms are dual vectors. Their basis vectors are dx mu, and there are n of these. NC1. Okay, this is NC0. Similarly, 2 forms The basis vectors are dx mu1, wedge dx mu2, and there are nc2 of these, and so on. Okay, so up till omega nm, which there's only one basis vector, dx1 wedge dx2 dot 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 wedge dxn. Okay, and there's again only one of these. So it basically goes on increasing till r is equal to n by 2, and then it goes then starts decreasing. Okay, because the number of indices that you can choose independently decreases. Okay, so this gives us a basis of one form, 0 forms, 1 forms, 2 forms, so on till n forms. Okay, once I go beyond n forms, that is, if I try to choose anything greater than r, okay, so if I try to construct dx1 wedge dx2 wedge dot 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 dxr, and now if I try to construct something else, okay, if I've already exceeded n, then there's no way I can choose this index, okay, of the r plus 1th index, okay, because I've already used them up here, and by the total anti-symmetry, if I choose one of these old indices again over here, then this will be 0. Okay, so therefore there are no forms beyond omega n, okay, where n is the dimension of the manifold. Okay, unlike tensors, so tensors, till you can have tensors of arbitrary rank, right? You can have tensors of 0m on the manifold M, and these tensors can go up to m greater than n. But here forms only go up till rank n. Okay, now let's consider something else. So let's consider the wedge product, okay, omega wedge psi. So let's assume that omega is an R1 form and psi is an R2 form. So this acts on, this wedge product should give me an R1 plus R2 form. So which means it takes in R1 plus R2 vectors. Okay, and by definition, this is the anti-symmetrizer acting on omega wedge psi, omega tensor product psi, times this convention factor R1 plus R2 factorial by R1 factorial R2 factorial, acting on V1 through VR1 plus R2. Okay. Now it's quite easy to show. I'll leave this as a homework exercise. It's one step to show this. Okay, that this is equal to 1 over R1 factorial R2 factorial summation over the permutations, where the permutations are over R1 plus R2 elements. Okay, minus 1 time, I mean, this is the sign of the permutation, times omega acting on the first R1 objects when I permute all of these objects. Okay, tensor product, this is not a wedge product, tensor product psi acting on the remaining objects from R1 plus 1 to R2, R1 plus R2. Permutation of R1 plus R2. Okay, so here is just a regular tensor product. Okay, so this is just basically how to write the wedge product of omega wedge psi in terms of the individual actions of omega and psi, okay, on permutations of these objects. Okay, and as I've already told you, if R1 plus R2 is greater than n, then omega wedge psi is automatically 0. Okay. Okay, now what you can do is we define these individual spaces, omega 0, omega 1, omega 2, omega 3, dot, 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 all the way up to omega n, okay, on the manifold. But what you can do is now you can generalize this with the combination of these operations, plus and the wedge product. Okay, you can talk about a linear combination of all of these spaces. Okay, so these are different vector spaces, and you can take a linear combination of all of them. Okay, and the linear combination of all of them gives you the space of all forms, okay, on M. Okay, so this is a sum of okay, it will look something like there is a general 1 form here, plus a general 2 form here, plus a general 3 form here, plus dot dot dot, plus a general n form here. Okay. And what you can do is now you can add, obviously you can add two objects in this space. So for example, if I have psi1 plus psi2 plus psi3 plus dot 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 plus psi n. I can always add these two objects, and by adding them, I will add individually within each subclass, okay, of forms. But I can also perform I can also perform multiplication of these two objects. Okay, so instead of just adding these two objects, I can also take a wedge product of these two objects. Okay, and that will give me something back in the same space. So what it does is it takes, for example, the omega. So it will take omega 1, and I will take the wedge product of this with this with this. Sorry, there's also omega 0. Okay, so psi 0. I will take the wedge product of omega 1 with everything here. So omega 1 wedge psi 0 will give me an object of type what? What kind of form is this?
One form.
This will be a one form. So when I take the wedge product, okay, I will add up all the one forms I get from taking these wedge products. Okay, so can you tell me what that full list will be? What will I get in the slot for one forms? This is one possible one form. What are the other possible one forms when I take the wedge product of this whole object with this whole object?
Omega 0 tensor product is epsilon 1
Wedge
plus
product.
wedge product plus omega 1 wedge product epsilon 0.
Right. This combination. Right. What about in the 0 0 slot? What do I get when I take the wedge product?
Omega 0 wedge product epsilon 0.
Yeah, but the wedge product is just the tensor product in that case because these are just functions. Okay. What about in the 2 slot type 0 2 tensors or type 2 forms? What will I get?
So 3 terms: omega 0 wedge product epsilon 2, omega 1 wedge product epsilon 1, and omega 2 wedge product epsilon 0.
Yeah, very good. Okay. So similarly, you'll get more terms. And any wedge product, for example, of let's say omega n with something else. Okay. Basically, if I cross n, then that wedge product is automatically 0. Okay, so I don't worry about this. So you see that this space, okay, the space of all the forms, okay, is closed under this combination of addition and wedge products. Okay, so you can define this addition and wedge products in the space of all forms. Okay. Okay. So some more properties, okay, of these forms. So if xi is a Q form, theta is an R form, omega is an S form. So the first thing is xi wedge xi is 0 if Q is odd. Okay. So xi wedge itself is 0. Okay, if Q is odd. So that is if I am taking, for example, D. I mean, that's easy to see by the total anti-symmetry of this, right? Because it's xi, tensor xi, and then anti-symmetrize. Okay? But this tensor product is already symmetric, so anti-symmetrization of this will give me 0. Okay, so this is xi wedge xi is proportional to this. So this is 0. Okay. Sorry, this is 0. Okay, let me be a little more careful here. Okay, this is 0 only if this is a type Q tensor where Q is odd. It's not 0 if Q is even. Okay. The reason being, okay, so let me write it out in components. Okay, so for example, if I have dx mu1, okay, wedge dx mu1, this is obviously 0 because we've seen that this is minus dx mu2 wedge, sorry, minus dx mu2. And these indices are the same, so this is equal to minus itself, and this therefore it must be 0. Okay, so in the case where xi is a one form, okay, we see that xi with xi is 0. Okay, but if xi is a two form, so we already have this something like this, dx mu1 wedge dx mu2. Okay, and now we take the wedge product of this with itself. This should also be 0, right? Because this okay, no. So this is not 0 because now it's associative, okay? But now what we have is this is dx mu1 wedge dx mu2, and again the ordering doesn't matter. I mean, in the sense of order of the brackets, okay, which operation I perform first doesn't matter. So this is what I have. But now if I exchange this, then this is minus, I'll get dx mu1 wedge dx mu2. Oh, sorry, I think I needed to be more general here. Yeah, okay, sorry. I needed to be more general here about the choice of Xi. Okay, it'll become clear in a moment why that's true. So for example, if I have a general Xi, okay, which I can write as it's some kind of Q form. So I'll write it as Xi mu1 through mu q dx1 tensor dx mu1 dx mu2 dx mu q. Okay, so when I take the wedge product of this with itself, what is going to happen is that I will get, so for example, if I take two forms, so if I take dx mu1, the coefficients are psi mu1 to dx mu1, dx mu2, and I'll write tensor dx nu1 tensor dx nu2, and I'll write xi nu1 nu2 here. Okay, this is what I mean by the tensor product of xi with itself. Okay, and now you see that that for example the term like dx1 dx2, but if I also have something like dx3 dx4, okay, this kind of term will come with the coefficient psi1 2 from here and psi3 4 from here. Okay, and therefore this term will be non-zero, okay, in general. But if I consider another combination, okay, that is, what if I had taken dx4 dx3? Okay, well, that would have come with the coefficient psi4 3, and this is anti-symmetric. Okay, this is anti-symmetric, so I can exchange the 3 4 indices and I can exchange these two indices here. So I'll get 3 4. Okay, and then I can add these together. Okay. Yeah. So basically in that case, xi with xi would be non-zero. Okay. So only if q is odd is xi with xi going to be 0. Okay. In fact, what you can show is xi wedge eta is equal to -1 raised to q times r. Okay. If this is a type q and this is type r, it's -1 raised to qr eta with xi, where I move the eta past xi. And roughly the way to think about it is when I want to move this eta past xi, if you think about it in terms of indices, this has q indices, this has, this has r indices, this has q indices. I want to move each of these r indices past every one of these q indices. Every time I perform an exchange of one of these r indices with one of these q indices, I pick up a minus sign. So that's why the overall sign is -1 raised to q times r. Okay, is this clear?
So this second property, can you explain once?
Yeah, so when I have a general thing like this, right? So what I'm trying to do is mu q eta mu1 mu r dx Okay, so okay, maybe it's easier to show this without. Maybe it's easier if I show this, using the general definition of psi wedge eta. So this is the anti-symmetrization of psi tensor eta with a 1 by with a q plus r factorial over q factorial r factorial. Okay, and eta wedge psi is q plus r factorial by q factorial r factorial anti-symmetrization of eta wedge psi, eta tensor product psi. Okay, now the difference between these two, okay, the difference between these two anti-symmetrizations is going to be this sign -1 raised to q plus r. Okay, and the reason is how to explain this using indices. Yeah, roughly. Okay, let me say this roughly, and then let me maybe make it more precise later. So what I want to do is I have these indices mu1 through mu r. Okay, and I have dx mu1 through dx mu r. Okay, now instead of thinking about the wedge product as the anti-symmetrization here, let me convert these to tensor products. And let me write this as an anti-symmetrization on the indices. Okay, this is equivalent to basically doing, as we've seen, 1 over r factorial psi mu1 through mu r dx mu1. Okay, something like this. So now basically this is just a plain old permutation on the indices. Okay, with regular tensor products rather than wedge products. And now what we want to do is we want to take psi tensor eta, okay, which will be something like mu1 through mu r. And then I have dx nu1 tensor product dx nu r, where I have eta now nu1 through nu r. And now what we want to do is perform a further anti-symmetrization. That further anti-symmetrization will be a complete anti-symmetrization of these two, okay, of these two pairs of indices. Yeah, okay, this will be equivalent to a full anti-symmetrization over these two pairs of indices. What we would like to do is we would like to relate this to some combination like this. Okay, so now I'm doing eta with psi. So I have dx nu1 nu, sorry, this is q forms. Psi mu1 through mu r dx mu1 dx mu r. Now the ordering here matters, okay, but these are dummy indices, which means that this new one I can replace by a mu one. Okay, this new q I can replace by new q. Okay, well, okay. What I really want to say is now that I want to match coefficients here. Okay, I want to match the coefficients here with the coefficients here. Okay, and relate them. Okay, I want the coefficient of, let's say, this particular some particular term in this tensor product. Okay, now what I will do in that case is I want to locate the coefficient of, let's say, dx1 tensor, dx2 tensor, dx3 tensor, dx4. Okay, I only need to look at totally anti-symmetric combinations, which means each of these has to be chosen uniquely. Okay, and so I want to locate that combination here, and I want to locate that combination here. That combination here, for example, if I take x1, x2, x3, x4, Okay, will be something like psi 1, 2, eta 3, 4, or something like that. And over here, it'll be, but it'll be other anti-symmetric combinations also. So it'll be terms like plus psi, let's say psi 2, 1, eta 4, 3, or something like that. Okay, so you'll have all these kind of terms over here. What I wanted to say is that roughly when to get these two, to find the relationship between these two coefficients, you have to move these q indices, mu1 through mu q, you have to move them past these mu1 through mu r indices. Okay, and when I cyclically, sort of, not cyclically, by making exchanges, mu1 moves here by exchanging with mu r, then mu1 moves here after exchanging with mu r minus 1, and then so on, till I bring mu1 here. Okay, and so on. Okay, so if by going on making these exchanges, so that is, if I want to move these new ones past all of these, and I want to move these new r's past all of these, then what I would have to do is I would have to perform q times r exchanges. And every time I perform an exchange, I will get a minus sign, which is why you get this overall factor. Sorry, it's just a mess of indices. Maybe we can work it out explicitly later. Otherwise, I mean, it's just cumbersome to show, with all these indices. Did the rough idea make sense, or maybe we can work it out later if it's not clear?
Okay, something.
Okay, sorry. Yeah, I'll try to explain it again later. Okay, so here's an example. We'll do a couple of examples of forms. Okay, so let's do, suppose we are in R2. Okay, we have two coordinates x, y. So the unique two forms that we have are dx wedge dy. This is the unique basis for two forms. Okay, and this is dx tensor product dy minus dy tensor product dx. This is, we will see that later. We can think of this as an oriented area element. Okay, that is, if you think about the area element, I mean, of course, these are dual vectors, but we'll see that this is related to thinking about this area element with side dx and dy. Okay, and it's an oriented area element in the sense that dx dy is sort of one orientation, and dy dx is another orientation. Okay, and this orientation is sort of opposite in sign to this orientation. So when I add them with a minus sign, they add up together. Okay. And similarly, in polar coordinates, okay, you can show that the same thing can be expressed in polar coordinates. Okay, this is just a two form. It can be expressed as r dr wedge d theta, okay, which can be written as r dr tensor d theta minus d theta tensor dr. Okay, so we'll see the utility of these forms later. Okay, so one of the things I told you is on manifolds you can define differentiation, and we've seen two notions of derivatives, right? We've seen derivatives using Lie derivatives, but we've also seen derivatives using some, if you define a connection on a manifold, which is some additional structure, we've seen that you can have some additional kind of affine derivative. Okay, we'll see that on these, using these differential forms, you can first of all define differentiation on differential forms, okay, which is slightly different from either of these derivatives. And you can also define integration on the manifold using differential forms. Okay, so that is something that I told you that we will look at later, which is how do you define integration on manifolds. Okay, and to define integration on manifolds, you need to talk about these objects, these differential forms, which is why we've introduced them. Okay. But the integration we'll only see in a later class. Okay, how to use them as for integration. Okay, so yeah, maybe we'll stop at this point. Okay, and we'll resume on Monday again at 4 p.m. Any questions here?
Sir, one thing like for any general n form, we so like we will write that simply as the we'll anti-symmetrize the coefficient, and those basis vectors will just be the usual tensor product.
For any general n form. So what do you mean?
Like which belongs to omega n space.
N form or R form? R is invention.
Yeah, yeah.
Okay, any general R form.
Or like so if omega belongs to the yeah, or xi, then we will write xi as, so we will anti-symmetrize these coefficients, and this basis will either this, or like as we're writing, or like
Yeah, this is equal to xi, where I now anti-symmetrize the coefficients and I take regular tensor products on the derivatives um, on the one forms. These are equivalent.
mm. Okay.
In a book like Wald, okay, which is here, you will typically see something like this, where they only talk about the coefficients and they talk about anti-symmetrization of the coefficients.
So like what is the reference of this?
Oh, this, sorry, should have said at the beginning. So all of this is from Nakahara, chapter 5. Just resuming after Lie derivatives. Okay, so the next class, what we'll do is we'll first talk about differentiation. Okay, some new derivative operator which we define specifically on forms. And so we'll talk about this for maybe next class and maybe a little bit of the class after that. And then in 2 classes from now, we'll talk about integration of differential forms. Okay, and this will actually lead to the notion of integration on a manifold and what we mean by that. And this is actually quite critical if you want to talk about, for example, let's say the action in general relativity, rather than talking about the equations of motion. The action is expressed as some integral on the manifold, okay, which involves the metric. And you typically have to define the action using some kind of volume element. And this volume element is a generalization of this area element in R2. And so when you consider this volume element, okay, it looks something like this. The volume element with a metric. Okay, so in order to think about this as the area, you need to have a metric on the space. So when you put a metric on the space, then this becomes your volume element. And if I want to integrate over the manifold, you have to integrate knowing what the measure is. Okay, so this is the volume element or measure of the space. Okay, and this is quite critical if you want to define any kind of action in general relativity. Okay, so these two ideas are what we're going to focus on: differentiation and integration of differential forms.
Sir, just one thing. This root minus g d4x is the covariant volume in arbitrary spacetime.
Mm-hmm. Yeah.
So like I have like seen this things have also like worked, but like without knowing this notion of integration.
Yeah, we'll show this.
Okay.
We'll show why that's the volume element, where this small g is determinant of the metric. Okay. Okay, let's stop here. We'll meet next week, Monday at 4 p.m.
Thank you, sir.
Okay, bye.
Thank you, sir.